The cost of healthcare has become a national concern in Canada as healthcare expenditures are rising rapidly, and with a large portion of the population aging, we're finding a disproportionate amount of healthcare funding spent on the aging portion of the population, as can be seen in the figures here. So our research focuses on applying currently available health communications infrastructure and networking technology, as well as emerging technologies such as the smartphone platform, which provides a powerful platform for application development. We'd like to combine and integrate these technologies to provide mobile patient monitoring and remote healthcare. So we collect medical information through the use of biosensor devices, which can then be transmitted using local body area networks enabled through technologies such as Bluetooth. We can then perform simple analysis on device with the rapidly increasing computing power of smartphone devices. We can then transmit data using existing communication infrastructure to healthcare professional operated servers for automated or manual analysis.
Our solution uses a personal area network, particularly utilizing Bluetooth wireless connectivity, to collect patient vital signs from wireless-enabled sensors coupled with a smartphone device. The smartphone will be running an application that performs automated analysis of the data and forwards data that may be of interest to a server accessible by healthcare professionals. Particularly alarming vital signs will trigger the application to take necessary courses of action. This may include calling an ambulance and providing the location of the patient, which is enabled by GPS technology.
Here is a working build of our application and the server. Our application focuses on the electrocardiogram, or ECG, signal, which measures electrical activity across the heart. The ECG signal is one of the most important physiological signals, as cardiovascular disease is the leading cause of death in Canada. The application can receive ECG data in real time through a Bluetooth wireless link. Simple analysis and feature recognition is then automatically performed by the application. The signal can be plotted in real time. The signal data is then aggregated and stored locally on the device. Metrics for when data is to be transmitted automatically can be defined. For instance, the signal can be transmitted if the heart rate exceeds a predefined threshold. The server consists of a customized front-end application to interact with the smartphone app or other authorized clients, and a database server. Currently, we're using the MySQL relational database server for managing data. The system enables powerful data management capabilities as well as flexible access to patient data through desktop and mobile clients.
Demonstration is of our IEEE 802.11 based reliable indoor positioning system.
In indoor environments, position location technology such as the global positioning system are unreliable as signal strength is weak indoors, and GPS receivers require a direct line of sight to 4 GPS satellites. This research project aims to provide reliable indoor position location using IEEE 802.11 or Wi-Fi infrastructure. Our system consists of fixed reference stations and mobile target nodes. The target stations, shown here, are Wi-Fi access points similar to those deployed in office buildings, business establishments, campuses, homes, and many other locations. The target node, whose location is to be determined by our system, will be a standard Wi-Fi enabled device, such as a laptop computer or mobile phone. Many indoor positioning systems described in the literature and implemented in industry are based on received signal strength indication based methods. Our system, however, is based on the time of arrival method. Our time of arrival method can produce more precise measurements and results in measurements that scale linearly with increasing distance. In addition, our system requires no customization based on the environment in which it is deployed. The output of our system while running is displayed in the top right window. The system alternates communication of the target node between reference stations and estimates the corresponding distance. The distance estimate is within approximately 2 meters accuracy. Using the reference nodes to form a frame of reference, the coordinates of the target node can be determined. Our solution provides an integration of communication and positioning technology using the same infrastructure. The location of nodes in a network can be used in emerging communication systems, such as mobile ad hoc networks and vehicular ad hoc networks, to support position-based adaptive communication. as the location of nodes in the network can be used to determine the topology of the ad hoc network. This demonstration is a field-programmable gate array-based prototype that is able to measure the distance between two communicating stations. This is a fundamental element of a wireless position location system. The method used here is to estimate the signal round-trip propagation time between the two communicating stations. The system consists of two parts, a master station and a slave station, both implemented onto identical field-programmable gate array boards. The master station is implemented on the FPGA board in the PC to the right, whereas the slave station is implemented on the FPGA board within the PC to the left. A periodic signal is generated by the master station and sent to the remote slave station. The master station marks the leaving time of the signal based on the local time reference. The transmitted signal is then relayed by the slave station back to the master station, with the arriving time of the relayed signal also timestamped by the master station. With these two timestamps, the distance between the two stations can be calculated. The yellow signal on the scope is the looped back signal from the slave station to the master station. The blue signal is the detected correlation peaks of both transmitted and received waveforms at the master station. The gap between the two peaks in the blue signal indicates the round-trip time of the signal, which is then used to compute the distance between the two stations. The design of the master and slave station are shown by the right and leftmost PC screens respectively.